Hello, myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. We have discussed many different aspects on metallic glasses, amorphous alloys or bulk metallic glasses, and today we will continue the discussion and try to specifically emphasize on their mechanical properties. Now, to understand mechanical properties, we must try to learn the physics of deformation in glassy or disordered solids. In this particular aspect, there are some theoretical model has been illustrated quite long time back. So, Professor Ali Argon from MIT was trying to create a model to explain the atomic scale mechanism on deformation in disordered solid. So, he proposed a theory which is known as bubble raft theory. In this particular theory, he tried to explain that the disordered solid could be deformed by some atomic scale rearrangement, and this particular rearrangement could be two major types. One is known as diffused shear, because a atomic scale cluster must be rearranged by some shearing event. So, this is one part which is called as diffuse shear, and the second one is the concentrated shear. Okay. So, in the left hand side, this model is shown here that there are several atoms which are randomly arranged, and if we think about such a cluster and give us a shear strain, then upon application of the shear stress, some strain will be generated which is the gamma, and here this is the net amount of shear strain has been given to that cluster. Now, please have a look to the right hand side of the slide. Here this is another same cluster which is shown here. We apply again a shear stress, and the mostly shear is concentrated between these two, not really parallel, but somewhat like that is concentrated, and it is known as the concentrated shear. Here also the initial arrangement of the cluster is shown here, and after the shearing event the arrangement or rearrangement is shown here. So, here you see the bottom part and the top part, they shear against each other, and the shear is concentrated mostly in these two different, let us say, layer of atoms. Even though these layers are not very regular like a conventional crystalline lattice. However, whether it is a diffused shear, diffused means the strain is almost distributed, or where here it is concentrated, this net strain to generate, there is a strain rate required. So, strain rate is explained with gamma dot. Now, it shows a Arrhenius type of relationship, And so, Arrhenius type of relationship means there is a constant and exponential, and definitely there is a delta G of shear, which is the activation energy of the shearing process, and this is the constant temperature at deformation, and K is basically a Boltzmann constant. Now, we need to learn something from here. We are talking about the shear strain, and a shear strain rate is generated during a very short time in a very localized way. However, this particular term, which is the activation energy of this shearing event, is linked with a constant which is C s, and tau s is a critical stress that is required for the shear to occur, and this cluster of atom which get activated during shearing process, it has a characteristic volume that is the net volume of this particular cluster, that is omega s. And it has been also proposed by Professor Argonne that even though we see this diffused or concentrated shear, but at any temperature or deformation temperature, the shearing event has two different components. Both the component may be active. However, the relative contribution of this individual component could be different. Like if the temperature is higher, here a higher temperature of deformation in case of glassy solid means the temperature close to glass transition temperature. In that particular temperature of deformation, the diffuse shear become more and more active, okay? Because all the atom get some activation energy and try to rearrange themselves, or the net activation energy of the whole cluster could shear. Whereas, concentrated shear is mostly preferred at relatively low temperature. So, let us assume that for a particular glass forming composition, if that glass has a glass transition temperature of somewhat like 400 degree centigrade, and if we try to deform at room temperature of 25 degree centigrade, then concentrated shear is mostly preferred, or the contribution of the diffuse shear is less. However, this is a bubble wrap theory, and which has been modified later on with the name of shear transformation zone, or STZ theory by Langer and Professor Falk. And there are several theoreticians who keep on doing several modeling experiments and trying to explain this particular feature. So, it is not only valid for bulk metallic glasses, but also metallic glasses or any other solid which exhibit amorphous structure or disordered atomic structures. And so, if we adopt such kind of understanding in case of a glassy solid, then since we talked about shear strain rate, so temperature and strain rate, both these parameters or external variables must be very much important on the mechanism of deformation. And a shear strain rate that is applied to a solid, however, a strain rate that is generated inside those atomic clusters, which may not be same by the imposed strain rate. And along this direction, if we simply take a supercooled liquid, even though the viscosity is higher than the conventional liquid, a supercooled liquid has a higher viscosity level than the conventional liquid, but we can think about a Newtonian or non-Newtonian type of flow. So, in that particular aspect, we know that a strain rate that is equals to A into tau to the power n. So, here this is the shear stress, and n is a exponent. If this value is n is equal to 1, then the strain rate that is inside the material is proportional to the shear stress, and we can reach to a very high elongation level. And if n is not equals to 1, then we get basically a non-Newtonian type of flow behavior. And if we look at the same in a plot, it also explain the same feature, that if we keep on increasing the temperature, then definitely we reach to a Newtonian flow, okay, where very large plastic deformation can be achieved. However, if the temperature goes down, then a non-Newtonian type of flow is activated. On the other hand, if we apply a very higher strain rate to a solid, then the strain will be localized into some clusters, and shear will be localized in those clusters. Okay. The cluster could be in a supercooled liquid, or the cluster could be in a glassy state, okay, in a solid. So, it does not matter. So, there is some transition from a shear localization to a Newtonian type of flow. It depends on the parameter, that is temperature of deformation and strain rate of deformation. So, this is a very good understanding we explored. And on the other hand, a non-Newtonian type of flow is also lead to very low amount of plastic deformation that can be achieved in a solid. And definitely, if strain is localized or shear is localized, then also we will get much or very less strain. Like if we think about a conventional crystalline steel, and then if there is some necking is also a localized deformation, just as an example. Okay. And so, let us try to proceed with this understanding and see that if we could categorize various type of deformation mechanism that is operative in a glassy solid. So, so far we understood that the flow in a glass could be homogeneous. So, this homogeneous flow could be two major types. The first one is a steady state flow, and the second one is non steady state flow. In case of a steady state flow, we could think about a viscous flow of the supercooled liquid. So, why it is important? So, if the temperature is very close to glass transition temperature near Tg, and definitely it will help in shaping the bulk metallic glasses, like conventional oxide glasses or window glasses. If we take and if we can blow a glass, then we can make different type of shapes like a bottle. Okay. So, for a bottle making process in a glass blowing shop, if you visit, then you will see that there is a die, and they put some oxide glass, and they simply put some air pressure at a temperature very close to glass transition temperature, where the viscous flow of this glass will occur, and it will take the shape of that particular pattern, okay, and or a mold. So, that shaping of glasses could be also very much important. Or let us say, if you like to make a micro gear means a gear with a teeth size somewhat in the scale of few micron, then you may not be able to directly cast, or even if it is not possible, then you can go for shaping, okay, or microforming. Okay. So, working on a glass required such kind of flow, and it should be homogeneous. Otherwise, if it is inhomogeneous, localized deformation occur, then there will be a failure in the material. And therefore, the steady state flow means there is some process goes on during deformation of a solid. Now, if we look at the Argon's bubble wrap theory or shear transformation zone theory, a atomic rearrangement can only happen when there is a local expansion of that particular cluster, so that atom get a space to rearrange themselves, and also again the structure should be relaxed to come back to a more dense form. Okay. So, in that particular case we may think about the local ordering or disordering process which goes on. So, like a continuous process during deformation at a given temperature, there is some structural ordering or disordering goes on, and there is some particular rate, they goes on at a particular rate. So, steady state can only be reached when this rate is equal. So, we can also think about there are some excess volume in the glass, and to rearrange a particular short range order or short range order cluster with hundred of thousands of atoms, then the free volume need to be increased so that atoms can rearrange themselves to a different configuration under stress, and therefore, the free volume creation is required. At the same time, once this particular shedding event completed, then there is also some localized annihilation process goes on, annihilation of the free volume, okay. Annihilation of the free volume, or on the other way, creation of the free volume means local dilation process, means expansion, as well as there should be some contraction. So, these the same process, there is some, they go on some rate during deformation, and this rate, if this rate is equal in a solid, then it can reach to some steady state flow, where the required stress to flow is almost constant. That is the understanding, and this only happen when there is a localized redistribution of the stresses, because once the stress is applied, some cluster where the stress concentration goes on higher and they rearrange themselves, again the stress relaxes. So, not only in terms of free volume creation, free volume annihilation, their rate to be equal, we can reach to a certain steady state. So, we can mathematically express such a steady state flow in terms of a shear transformation zone rate, S is rate, which is S dot, which is nu, which is some sort of frequency, and there is some exponential Arrhenius type of term. Here Q is basically the activation energy, and you can see here I wrote this volume is the activation volume and some stress with plus minus signature. What I want to mean that the required activation volume could be modified by application of the stress. Modified means it could increase or decrease. So, let us say a particular shear transformation zone may get favored, or a atomic scale cluster may favor to undergo a shear transformation by the application of stress, okay, or it could be retarded by the application of stress. So, in that case the activation energy will increase, which retard by the application of stress, or it could simply decrease by the application of stress, and that is why I put here a plus minus term, means there are some phase shear transformation in some cluster which is favored by the applied shear stress. And so, we can get a mathematical expression in terms of such a steady state flow. However, if all these explanation that we understood in terms of local dilation or relaxation, if they are not equal, then definitely a non-steady state flow can be seen, where there is no balance between any of these processes, okay, and because of the rates are not equal. And now, like homogeneous flow, we have also inhomogeneous flow. So, these are the two major types actually, and inhomogeneous flow means that there is some localized deformation, and localized deformation means the shear strain is accumulated in some specific sites in the glassy structure. So, at that time the shear localization occur and it lead to the formation of some bands, because bands means atomic or let us say some planes or some zones where the shear strains are more and more localized and they relieve the stress at the surface, and we can see such banded structure. In the next couple of slides, I will show you how is the appearance of the shear band in a glassy solid. And since the stress is localized, some part of the work must be converted into the temperature. Okay. And therefore, there is some heat evolution in the shear bands, and these are some of the important aspects of today's discussion. Now, let us have a look at some of the deformation curve of one zirconium based metallic glasses. This is also one derivative of vitralloy, and the temperature is kept somewhat around 370 degree centigrade, where you can see that the T by T g is 1.03, and it means that the temperature is very close to the glass transition temperature. Now, let us have a look at the stress strain plot, which is very important. And during this experiment, the strain rate has been kept at 10 to the power minus 3 per second. And here the stress increases and remain almost similar with increase of strain. So, this is something like 25%. There is no change in the flow stress level. Now, it has increased, let us say 5 times, and so in that particular case there is a slight overshoot of the stress, and then again the flow stress remain constant with further deformation. In this case, it is basically 10 times higher than this strain rate, and so almost 1 order magnitude higher strain rate is applied. In that particular strain rate, we see a very significant overshoot of the stress initially occurred, and then there is an undershoot, and then again flow stress remain constant. So, this undershooting or overshooting is somehow linked with non-steady state flow. Non-steady state occur when free volume creation and annihilation or local dilation and relaxation are not in the same rate. So, initially when deformation proceed, then free volume increases, and the increasing rate is higher with increase of the strain rate level, and once it reaches to a peak value, then basically the undershoot occur due to the opposite process goes on, and after some percentage of strain, both the process come in a balance, and due to that particular balance we get a constant flow stress, and therefore, this is a region when steady state flow is there, and here this is the domain when we can see the non steady state flow, and this is a very clear and very common example of a disordered solid for particular this type of flow. Now, let us take the same glass and deform it at this particular strain rate. We see such kind of slight overshoot, and then there is a steady state is reached here, and now suddenly if I change the strain rate. Okay. So, definitely it will go here, because these are somewhat in the same scale, and then again it will reach to, there will be undershooting and there will be some steady flow, and then again I go back to the initial strain rate, which is lower than this particular one. Okay. And then again I can see that the steady state could be reached in that particular level. It means that the material flow stress is somehow linked with the given strain rate, or material remember the flow stress which is a function of a given strain rate, and so it is something like a memory effect in a glassy solid. So, these are particular deformation mechanism people try to understand by varying deformation temperature and strain rate. Now, let us come to the inhomogeneous type of flow. So, here once again a derivative of vitrioalloy glass was taken and they kept under compression. So, for doing this compression, we basically take such kind of height, which is the height of the sample, and there are some diameter. Cylindrical samples you can take, and we monitor the variation of the stress and strain. Okay. So, this is something like 2% level here. So, we can see that the material yielded showing a elastic strain of somewhat in the level of 2%, okay, which is almost 2 or 3 times higher than any conventional crystalline alloy. So, very high elastic strain limit that can be achieved. However, even though there is little plastic deformation of less than 1%, but if you magnify such deformation such stress strain plot, you will see that there are some small serrations type of behavior, and this serration must be linked with the localized strain burst, means must be somewhere a sudden strain appear and that is linked with again some requires some activation, and then again there is some flow and there is a drop, that is a undershoot, again some overshoot, again some undershoot, overshoot, undershoot, and so on. Okay. So, formation of such kind of serration clearly indicate that this is definitely not at all a homogeneous flow, but it is a localized flow event or a inhomogeneous flow event that goes on in a bulk metallic glass. Now, very similar type of behavior people have also observed in case of a nano indentation. So, there during nano indentation, since it is a instrumented indentation means that we are capable of measuring the indentation depth with the given load or the strain rate. So, we can vary the loading rate. Here you can see, if you see the unit, it is basically millinewton per second. This means the loading rate has varied. So, load is a unit of millinewton per second. Here is also millinewton per second. So, higher loading rate means a higher strain rate is expected. So, at very higher strain rate, the serrations almost like vanish than the lower strain rate. So, which is expected. So, a higher loading rate where it appears to be like a homogeneous type of flow to the inhomogeneous is like a showing some sort of transition. Very similar way here also, this is a zirconium aluminum copper nickel aluminum glass, or let us say this is also one of the derivative of that kind of glasses. Here is also another palladium type of glasses. During nano indentation, people observe such kind of serrations, and these serrations are called as pop in event, and these pop in events are linked with the formation of some localized strain burst or the some shear bands or deformation bands in this glassy solid. So, today we tried to look at the atomic scale mechanism of glassy or amorphous or disordered solids. We tried to learn about the Argonne's model on bubble raft theory, also the shear transformation zone theory, and how the shear transformation get activated upon application of the shear stress or it may retarded, and we can simply think about the localized strain rate that evolve, and we try to understand what is homogeneous, inhomogeneous flow, and what is steady state can be reached, and how a non steady state can be reached. So, these are very fundamental understanding of any disordered solid, and the inhomogeneous flow and inhomogeneous deformation we will discuss in the next class. Thank you.